Okay, let's get started. So our last class, we walked through in fairly good detail about our induction motor, and we had developed in the class prior to that. Let me get this out of the way. In the class prior to that, we had developed the equivalent circuit, and then we said, let's do some analysis and see what we get for results using the equivalent circuit. So we're really going to pretty heavily rely on this equivalent circuit because we're actually going to be able to replicate our torque versus speed characteristics. So what we did in lab this week, where we actually varied the load, the applied torque on the machine, is actually how we would see how this machine would start to slow down. So we're going to investigate that a little further. We're going to do an equations, but remember, an equivalent circuit means that the results that we get doing circuit analysis should match pretty darn close to what we would see in the real world. And remember, in the real world, the way that we change the load on an induction motor is not by electrical, but by mechanical. You put more load or more torque demand on the shaft, and that's how you get more load. Yes, sir. The zoom. Oh, this thing. Okay. Sorry about that. I think these slides are uploaded, are they not? Are they not in the content folder? They are? Okay, thank you. I'm not doing that to pick on you. I'm just saying, did I do that? Because I've got so many things. So just remind me if I haven't uploaded them that you can find them there. So we put more mechanical load, and there's a bunch of different ways we can do that. If we are driving a fan, for example, so an induction motor is a great application for a fan, then we just need to move more air. One of the ways we move more air is we put bigger blades on the fan. So we can certainly put bigger blades. Naturally, it can happen. The air density can change. Or if we forget to change the filters, right? Anybody here live in a house with forced air heating system? And at the end of the winter time, the heat doesn't come out quite as well. Well, there are filters on that system. So if you don't clean your filters, right, that's the way that you would have increased mechanical load. That's not a desired characteristic. That just means you're too lazy to change the filters. But that's the actual application or idea that we would add more load. And in induction machines, as we move more and more into power electronics, they're getting cheaper and easier to manufacture. You can actually use power electronics to increase your load. You basically are increasing the synchronous speed to go ahead to get more load. What I mean by that is, we said that we have a 60 hertz, we have 1800 RPM, 3600 RPM, et cetera, et cetera. There's nothing saying the frequency of the motor can't be higher. That variable frequency drive takes input AC power, converts it to DC, and then outputs an AC electrical frequency, and you have unlimited control over that. You could run that down to 1 hertz, or if the drive is capable, up to 2000 hertz. So you could change your synchronous speed to whatever value you wanted it to be. And then correspondingly, you're going to increase the speed, which usually, not always, but usually increases the load that is demanded on something. Okay. So again, our mechanical engineering friends are the ones that are going to increase the load demand on our system. So now we're going to expand a little bit. Now, this is totally up to you. This approach of how to use to calculate torque and power using Thevenin's theorem is a way if you're going to calculate it manually every time. What we'll see if we use MATLAB, and that file that I uploaded on Tuesday has all the information, well, you can just do brute force. You can do enough calculations so that you can get the accurate results. Where with Thevenin's theorem, you have some approximations to simplify things down a little bit, but you get pretty good results nonetheless. All right, so we're going to look at a Thevenin equivalent, which means we want to find the Thevenin equivalent seen across these 2 points. So the concept of Thevenin equivalent, you can replace any set of elements by taking a voltage source or finding the open circuit voltage at that point. That's step 1. That's the Thevenin voltage. And then to find this Thevenin equivalent impedance, you look at the terminals and then you see the impedance that is reflected or exists there. And then that impedance in series with that open circuit voltage is your Thevenin equivalent. So I'm going to try to solve for the open circuit voltage at this point, and I'm going to look for the Thevenin equivalent impedance of this entire point A to B, which means these three elements I have to solve for the Thevenin equivalent impedance. So essentially what I'm doing is I'm going to replace this whole element here with a voltage and an impedance. So let's go ahead and do that. All right, so so the first thing I'm going to do, actually I did it on the other side. I'm going to replace these three, not these two, not these three, the ones to the left. So here's my Thevenin equivalent, and my voltage, again, is going to be across this terminal. So that's still applicable. And the reason why I'm interested here is because the amount of torque that is delivered to the machine is determined based on the current flow through that equivalent resistor, R2 over S. So what I want to do is I want to figure out very quickly and very efficiently how I can calculate that current. So here's my equivalent circuit. Now I solve for my voltage. Hopefully you can see over here that the voltage that I'm going to see here is going to be equal to, well, I can't talk today. I'm going to put these in parallel. Sorry, still dealing with a cough. And do my calculation. So I have this voltage, and I've got a voltage source. So the voltage that I'm going to, whoops, sorry about that. So the voltage that I'm seeing here is that impedance voltage divider. So that impedance over the sum of the impedances times the applied voltage. So I've got an applied voltage here. I'm going to use voltage divider to solve for the voltage drop across that element. And it's these three elements here. Now, does anybody have any heartburn with the fact that I didn't include those impedances? X2 and R2?
Yes, why didn't you do that?
Ah, very good question. Why didn't I do that? Because I'm looking for the Thevenin equivalent, which means I open circuit that, don't I? I'm looking for the open circuit at that point. So I don't include the rest of the circuit. I'm going to replace everything over here with a voltage in series with an impedance. Essentially, this is loading, right? Loading on my Thevenin equivalent that I will add after the fact. Exactly. So this voltage is V Thevenin, R Thevenin, X Thevenin. I haven't thrown away the X2 and the R2. I'm just adding them after the fact. So when you're doing Thevenin equivalent, go back to your circuits class, which says you open circuit and you look for the elements, you know, whatever you're trying to replace it with. I remove the load, that's just a load. I set that aside for the moment, and then I do my calculations to solve for V open circuit and Z Thevenin, okay? If you don't like drawing it that way, where's whiteboard? I don't see whiteboard, so we'll have to bring up whiteboard. Okay, while this is launching, my equivalent impedance. So here is, whoops, here is my resistor, my inductor, R1, JX1. This is JXM. This is JX2. And then I just have that one resistor, R2 over S. And normally these elements are in fact connected. But the whole thing about the Thevenin equivalent is I open circuit the terminals of what I'm looking for, and then I solve for the Thevenin equivalent. So as I said, this gets moved off to the side. So the only circuit I see, or the only elements of the circuit that I see, are these. And since I'm looking at this terminal point, I'm looking for V Thevenin and Z Thevenin. V Thevenin, hopefully you can see, is the voltage drop across JXM. That's voltage divider, right? So we do voltage divider. It's the applied voltage across the series elements multiplied by the impedance of interest divided by the sum of the impedances. That is the Thevenin. Does that ring a bell? Anything that you hadn't seen before?
It's ringing a bell.
Okay. I'm not trying to be sneaky. I want to make sure everybody understands. I don't throw away the R2 and the X2. I'm setting those aside because I'm just trying to find the Thevenin equivalent. And I can take anything, any part of the circuit I want, isolate that part, find the Thevenin equivalent, and put that back in, and I'm going to get the same results. That's the concept of Thevenin equivalence. How about finding Z Thevenin? What do I need to do to solve for Z Thevenin?
Turn off the sources of power.
Turn off the independent sources. And how do I turn off an ideal voltage source or an independent ideal voltage source? What's that? Short circuit? Open circuit? Anybody want to break the tie?
Short.
Short?
Yeah, short circuit.
I'll give you a hint. You actually aren't replacing it with an open and a short. Do you know what you're actually doing when you turn off a voltage source? No. You actually replace it by its equivalent internal impedance. An ideal voltage source. Okay. Here's the voltage. An ideal voltage source means the current, no matter how much load I draw, that voltage is always flat, correct? That's ideal. If I want to model any voltage source, here's my voltage, here's my internal impedance, and here is the voltage at the terminal, right? Any real world power source is going to be modeled as that. What does R in have to be equal to so that as I increase the load, that voltage drop never changes?
0.
What's that?
In an ideal, it would be 0, right?
Yeah. Isn't the only way to make sure that that voltage never changes as I increase the current is to make it 0. So when you do turning off an independent voltage source, you are replacing it by its internal equivalent impedance. Ideal voltage source is 0. So that's why you replace it with a short. Okay. So I wanted to develop, because one of the things that I think is always important is develop that deeper understanding of like, I replace it with a short. Why? I don't know why. Why would I replace it with a short? Well, you're basically just saying, put the impedance in there. You're literally turning it off by making this equal to 0. So that's a short, and you're putting in its internal impedance. It's the same thing with a current source. Let's look at the current source. This is I. And regardless of the load, I'm going to apply against a current source. And the only way that I can apply load against a current source is I'm going to expect it to deliver more voltage, right? So the only way that that can happen is, and again, I'm going to have a resistor in here, but it's not going to be in series. It has to be in parallel, because that current source, if I open circuit it, all the current should be flowing through here, right? That's the thing about a current source. You have to make sure that it continues to provide current. So to do this, what does Rn need to be equal to for it to be ideal?
Infinite.
Regardless of the voltage that is applied across it, the current here should always be equal to I. Or not 0, but I. This is constant.
It'd be infinite.
Yeah. If that's equal to infinity, how much current can go through there? So as I increase the voltage, I can put it up to 10 million volts, and current should never go through that parallel branch. So when you replace an ideal current source, you replace it with an open circuit. But it's actually replacing it by its internal impedance, which is here. Does that clarify things a little bit, or? You could say no, but. Well, how were you taught back in the day how to replace ideal voltage and current sources. So you were just basically told this is what you do. Yeah. But now you understand like why, because it could be like Basan pointed out. Why couldn't it be an open circuit? Because you told me it was a short circuit. Why couldn't it be an open circuit? Well, now you see why it can't be an open circuit, because what I see is infinite or zero resistance. Okay. All right. So now we're going to go back in. I almost swapped over. How do I replace that voltage source with a by turning it off? I replace it with its internal impedance. It's ideal, going to be equal to 0. So now what I'm left with, JX1, JXM, and I'm looking for the impedance in that terminal. Hopefully you can see that Z Thevenin is equal to JXM in parallel with the series combination of R1 plus JX1. So then I go back to my circuit, and those are my equations. I just call this Z Thevenin, but you know it has a real part and imaginary part, gets the same value. Okay. Now, for what it's worth, this one has some real parts and some imaginary parts. We can go ahead and convert this to a magnitude of voltage, and we'll see why getting the magnitude of voltage is important in a little bit. But we can solve for the magnitude of the voltage. The magnitude of JXM is just XM, right? Real part squared plus imaginary part squared, square rooted is just XM. In the denominator, R1 squared plus the two impedances, or sorry, reactances added together, squared, and then square rooted. So those are our magnitudes. All right, so this is where we have to start making some assumptions, because we have these two equations, which could be a lot of work to do some analysis. So let's try to simplify these down. And if you remember, my value of XM was much, much greater than X1, and was also much, much greater than R1. So if I look at this equation for my equation over here, my value of XM is going to dominate. And the same thing in the numerator here with my value of XM is going to dominate. So I can simplify and say that V Thevenin is going to be approximately, not exactly, but approximately equal to XM over X1 plus XM. Okay, get rid of the R1 value, and then don't worry about the complex numbers. All right, and then I don't have any phase shift, because again, that R1 value is going to be a negligible value. So we would anticipate essentially that we're going to get any phase shift. Similarly, our XM is much, much greater than X1, and X1M plus X1 is much, much greater. We're going to simplify our value for R Thevenin. Our value of R Thevenin is our initial R1 value times X1M over X1 plus XM squared. And then my X Thevenin value is going to be close enough to say that it's going to be equal to 1. Okay? Close enough that it's going to be equal to 1. So now,
to 1 or to X1?
1. Oh, X1, sorry. Yes.
Okay.
All right, so now my value of X2, so I go back to my diagram, and I'll just draw it over here instead of going up and down, because I don't want to keep bouncing around. Here is R1, here is JX1, here is JX2, and here is R2 over S, and the applied voltage I have over here is V Thevenin. Okay, that's the value that I have. So now this current, because this is just a series current, I no longer have X1 and X2. this current is the equivalent current flowing through in the rotor circuit. So my value of X2 can be found pretty easily by taking V Thevenin. And again, I'm going to just divide by the square root of my R plus my XM or my X, those values squared. So again, this is using this to be a magnitude number. I'm getting the magnitude of I2. Now my power converted, and you can see why I use magnitudes, because this equation right here, that has to be a magnitude only term, right? That has to be I2 magnitude, not I2 magnitude and angle, just the magnitude only. So I'm actually solving for the important parameters that I need. So my converted power, we derived this equation in class, 3I2 squared R2 times 1 minus S over S. And my torque is going to be either the converted power over my omega sub M or the air gap power over omega sub S. Either one is perfectly fine. So now I'm going to go ahead and substitute that equation, because over here I have my converted power, which is here, and I can divide this equation by omega sub M to get my induced torque, or I can substitute 1 minus S over S. So this one is doing the substitution of 1 minus S over S. So this is my 3 times my I2 squared times R2 over S times my value of S. And you can see, hopefully, that this 1 minus S term was divided out from over here. Okay, so that term is divided out. That's why you don't see the 1 minus S over here, and you don't see the 1 minus S over here. We just divide it out. And then getting rid of our square root terms and our square terms and moving things around. Here is the equation to calculate induced torque directly. So I can see that I've got a bunch of values of X and R and voltage. You remember in lab when I said, make sure you fix your voltage at 100% or 120 volts? Because look how my induced torque gets impacted. As I change that value of voltage, it impacts the actual torque by the square of that value. So a 10% change in voltage is going to affect it by 0.1 squared. It's going to reduce the torque by that much, right? So instead of 100% voltage, if I go 90% voltage, instead of getting the torque down by 90%, it's 0.81%, right? So a huge impact. That's why we needed to set our voltage to that value and leave it there. Otherwise, we'd get pretty wonky results. Doesn't that look awfully familiar? This curve, this induced curve, is how you build this particular value. And the only thing that changes in this curve, the R's don't change, the voltages don't change, is the slip, just like what we did in lab. So we have our starting torque, and we saw that this was a little bit steeper, and you can change the characteristic, but you know, it's pretty steep going up until you get to the full out torque, and then gets to the full load torque value. In lab, we were pretty close to being able to replicate this side, right? It's just that once we get really close to the pull-out torque, we'd lose it, and then we'd end up on the other side and be at some really slow speed of operation. So that's how that characteristic is made. And this is actually what happens in the real world. You can design, or you can adjust this a little bit, and we'll see how to do that in a little bit. But this is how we can change that. This is how we actually operate an induction motor. Yes, sir. Great question. Why is this 200%, 300%, et cetera, et cetera? Anybody want to guess? What if it's a 10 horsepower motor? It puts out a certain torque, right? What if it's 1,000 horsepower motor? Yeah, this is 100% of nominal torque output at the speed. But that could be for a 10 horsepower motor or a 1,000 horsepower motor. So I don't actually care about the numbers. I just know that the starting torque is about 2 times greater than the full load torque. And the pullout torque is around 450% of what the normal full load torque value is going to be. So you do it as a percent just to make it easier. Mechanical speed is also not shown either, right? It's just written as a value of synchronous speed. And we know that this is in synchronous speed. That is the nominal speed of operation. But our actual speed can vary anywhere up and down. Okay. So we talked a little bit about this in lab, but no torque when you're at synchronous speed. And that's the reason being is we have no dp/dt when the rotor and the stator field are spinning at the same point. That's the mechanical rotor and the electric field on the stator. They spin, there's no, at the same speed, there's no dp/dt. It's pretty linear between no load and full load. What that means is, I guess I'm gonna go back up here. It's pretty linear, like this line has a fairly constant slope. So if you're trying to figure out speed of operation, if you add more load or remove more load, you can predict pretty well without having to spend too much time what that speed will be, because you can do y equals mx plus speed. You can find the slope of the line and you can figure out for a 2 RPM speed change, you can get a torque or an approximate change in the torque. So there's pull-out torque. Don't worry about the numbers. 2 to 3 times. That curve shows 450%. It really depends on a bunch of factors. So sometimes it's 2 to 3 times, sometimes it's more. We'll actually see where we can change that a little bit. So we know that the motor torque at start is higher than its full load torque. And that's a good thing. Why is it a good thing? Because if you have a pump, and if the pump is not pumping, there's essentially no load. If you have a bunch of water sitting on it, it doesn't, it spins up because it starts to pump water. It can spin up pretty slowly, no big deal. But if you think about the fan, remember the example of the fan? Do fan blades seem like they're hard to start up? No? So remember, you only are controlling the shaft. You only have output on the shaft. That's 1 inch. What if the fan blade is 3 feet in diameter? And you only have a capability to locate in that 1 inch diameter. Get that thing to spin. Try it sometime. Just rotate on the shaft and see how hard that fan is to get it up to speed. Very, very difficult. So fans are actually some of the hardest things to get up to speed and rotate because they take so much inertia. Think of all that spinning inertia that's way out from the center of the shaft. It just takes a long time to start. So fans sometimes have special characteristics because they run under what's called lock rotor or heavy load conditions for up to a minute in some cases. Where a pump can spin up very quickly because if it's not pumping any water, it doesn't have any torque. And then as it gets more and more speed, it has to do more and more. So pumps usually can start pretty easy. Fans are a real struggle. And keep in mind, these aren't the box fans that you're going to buy at Walmart for $17, right? If this is a big motor, I mean, it's not unlikely to have 2 foot, 3 foot diameter, and it's not going to be made out of plastic. They're going to be made out of metal, right? Some sort of a steel. It's really fascinating. If you ever seen people when they make fan blades, you think it's real simple. It's actually really complicated. Anybody in the boating? That's the analogy I can think of. Think about a propeller. Anybody here have their propeller ever balanced? Come on, there's got to be an honest person in here who's run aground a couple times. And
Yeah, I've been there.
yeah, okay, thank you. What
I
happens
broke
when you
one
run
of the-
aground? You're trying to get too cute and you hit some rocks. Your propeller gets
Yeah, I broke one of the propeller blades off my prop, and then the other 2 only lasted like maybe another 100 yards or so before it just disassembled itself.
because it starts to because of vibration. I'm surprised it actually was able to stay on the shaft for I'm assuming it was an outboard, because once it's out of balance, remember it's spinning at 2, 3, 4,000 RPM. That's a tremendous amount of vibration. So any little bit of weight off will ruin it. Anybody here ever had their tires balanced? Driving down the road and the car is vibrating, and that's off by like 2, 3 ounces. And that's a 15-inch or 17-inch diameter tire. I mean, think about that in terms of something that is running, you know, with a missing blade. It makes a huge difference. So fan blades are really, they're pretty well designed and machined, and you know, some are made of aluminum. I don't know if they're all made of aluminum. Maybe aluminum is not strong enough. I know steel is a pretty common one, but I don't know that much about it. So yeah, fans are tough. Really tough to start. Anybody here ever work with a compressor, an air compressor? What's the last thing an air compressor does before it shuts down? Yeah, you'll actually hear it when it shuts off. You'll hear this psst, this really quick release of air, and that unloads the cylinder, because once the motor is running, it's pumping air into a chamber, okay, and that's compressing it. If you shut the motor off and you didn't release the pressure inside the cylinder, when that motor tries to start up, it has no inertia. Now you've got the cylinder that's sitting there that it could be putting there could be a tremendous amount of air pressure, 200-300 pounds, depending on what you set. Now it's going to overcome that 200-300 pounds of air pressure and push up on it. So one of the things you do, if you listen carefully, if you go to a place and you start up and shut down a compressor, you'll hear this really quick, this like release of air. And that's because the cylinders or the valve, well, yeah, probably the cylinders, not the actual storage cylinder, but the actual cylinder where they're doing the pumping, it releases the air so that you can start it back up again. You manually release yours? Yeah, it does. I like to do mine every once in a while. I'll just let it out, the water that's in the tank, and you just pull it out and it sounds like an explosion. What's that? I can't hear it, but I think if anybody here do automotive stuff, if you have a compressor, they tell you to drain the water out of it every month or two.
Yeah, the one we've got drains it automatically every it's almost like every hour.
It drains the water?
Yeah, it blows off the bottom of it every hour or so. It'll kick out of the bottom.
I'm surprised, because most of the time what they do is once they kick it off, they release pressure. So now your tank has lost pressure. So if you're spray painting a car and then all of a sudden you're hitting the gun and there's nothing because it just blasted out a bunch of air. But Ryan, you were saying, sorry? Yeah. Yeah, there's a lot of energy there. So you know, most people don't realize that, but there is a little valve on the bottom of, I think even cheap air compressors, because you know, it's regular air. And as you compress it, what happens? The condensation in the air compresses and it actually turns to water. And before you know it, you've got a ton of water in the bottom of your compressor. So food for thought. What's that? Don't blow up your garage. Yeah. So the torque of a motor for a given slip, this is a thing, it varies pretty significantly as you vary the voltage, the applied voltage. So one of the things that we don't do them as much as we used to, but really big motors, when you start them across the line, would actually trip because they draw too much current. Well, how do you fix that? You drop the voltage. It's called a reduced voltage start motor. And they used to be very common, they're very inexpensive, but you literally would drop the applied voltage and it takes less torque, which means it takes less current. So it takes longer for it to start up, but you don't need as much capability to start it. But voltage is huge. Biggest change. And this is how you get a wind turbine generator. If you can spin it faster than synchronous speed, then it creates energy. It's a generator, not a motor, it's a generator. So all those wind turbines, or most, not all, but they're called doubly fed induction generators. We'll talk about that in a little bit. But as long as you can get that blade or the shaft to spin at a faster rate than the actual magnetic field that is rotating along, you can generate electricity. And you need to do that for wind turbines because as we talked about in the other class, does the wind turbine always spin at a constant rate of speed? Better not, because there are times when it's running as a generator and the other time it's running as a fan, right? Constant speed would mean when the wind's good, it runs at that speed. But if this wind speed is too low, and if it's still spinning at the same speed, it's taking electricity in and spinning that at synchronous speed, which, believe it or not, those wind turbines could in fact do. Yes, so the question is, do you turn off wind turbines at too high of a speed? And the answer is 100% yes.
Yeah, you rotate the blades, right?
Yeah. So what wind turbines do is the way that a wind turbine is designed is it's designed with its blade angle of attack to capture the maximum amount of wind. And it does that, but as the wind speed picks up, it starts to increase its output power until it reaches rated value. And then at some point it levels off. And at that point, you start to feather the blade to shed some of the wind. But it'll still continue to run because it's able to shed enough speed. And at some point, if the wind speed continues to get too high, you actually will go so high that you can't safely shed speed. So you actually have to brake it. You have to apply a brake and force the turbine to shut down because you can't control the speed. And those tip speeds on a turbine blade, some of those are pushing the speed of sound, 400 or 500 miles an hour. Remember, the blades are 80 meters in diameter. So if it's spinning at 40 RPM, 50 RPM, by the time you go out 80 meters, that's ripping along pretty good. That's why most people don't realize, but you think, how can a bird run into that? Well, remember, if it's flying along, it doesn't see anything, and then something comes down at 500 equivalent miles an hour, it's pretty easy to see how you could miss that. So if it gets too high of a speed and it's going to be sustained, it's one thing if it's gusting, but if it's sustained, those turbines will actually fully feather their blades and they'll provide a brake, and it'll take a long time, but eventually they will shut down and they will be held in that position until they can restart. It doesn't happen that often, but it does happen. It's a great question. I imagine they can feather it any way they want as long as they have the actuators. But keep in mind, the blades are designed with all kinds of figuring out forces and stuff. If you start to over rotate them, it could be subjecting the blade to forces that are not anticipated, and you could damage the blade. These blades are made of fiberglass. They're not, I mean, they're elegant structures, but they're not, like 10,000 feet of concrete. I mean, if you want, you can walk over to the structures lab and see some of the blades that they have. They used to have them all back, but rotating them too much, it depends on the blade. And I can't answer more than that because it really is, that's a fluid dynamics. There's a whole lot involved with designing turbine blades. That's way beyond me. Nate actually, one of our classmates, he might actually have some insight because he designs things that run in water, and it's probably very similar. If the tide's too high, what do you do when the tide's too fast, Nate?
We stop the turbines because the drag's too high for the system as designed, and so you don't want to damage anything.
How do you stop it?
We either use a very high resistance load and install it electrically, and also we can use, and then you also short the windings because we have a synchronous motor.
Okay.
So you short the windings, and then we also have a mechanical brake.
Okay.
And then I've had others. We had a prototype system that had pitching foils, and you could actually make those foils go back and forth in different directions. And it was both a propeller and a turbine.
Yeah. So it works in either direction. So.
Yep.
But the design, even for maybe it's not as sophisticated. I don't know. Nate can comment on that. But the way that the water or the air travels over these things, it's really an elegant design. And if you think about, they're called horizontal axis wind turbines. The ones that are really close to the center are spinning at a different rate than the ones at the tips. So the designs are very different from the tip to the end of the blade. And I don't know if that's the same thing for the tidal ones. I'm not exactly sure, but there's a lot of design that gone into to optimize energy capture.
Yep, they're pretty much the same.
Yeah,
they work the same. They spin at slightly slower tip speed ratios.
Okay.
wind turbines are like 5 or 6.
Yeah.
Peak.
Yeah, and if you want to learn more about wind turbine stuff, ET460, for those of you who are entering in the fall 23 curriculum, that's a required class now. So if you haven't signed up for that curriculum yet, by the way, you know that some of you haven't taken differential equations. You don't have to for the fall 22 curriculum. Fall 23 curriculum is not required, but you'll take differential you'll take ET460, which also counts as population and environment elective, but it just releases one of the gen eds requirements that you have, or tech electives that you have to take. No, no. Whatever curriculum you came in with, that's the one you want. If you don't want to take differential equations, then you should switch now if you don't want to take 460. But if you pass it, then there's no incentive for you to do it. Yeah. So. Well, you could have still gotten it. You could switch now and you would give you a tech elective for it. Because you've already got differential equations, that would be moved to a tech elective now if you went into the new curriculum. No, if you move to the new curriculum, it counts.
You have to contact the School of Engineering Technology to switch curriculums, or?
Yes. Yeah, you can't do it through us. We don't have authority, which is probably a good thing. I tell everybody, if you want us to do administrative stuff, it's going to fail. We're not good at that. They're way better at that than we are. So we often ask them for help. They're great. They're way better, more competent than we are in many things. So
Yeah,
take
just
that
toss
torque
them an
versus
email.
speed characteristic, swap it around, and you got a generator. So remember how we talked about hybrid vehicles? Why do they work so well? Because that same piece of equipment, exactly the same piece of equipment, can operate as a motor or a generator. That reciprocating engine, you might be able to do a little bit of engine braking, but that's still just going to be waste energy. So you're using it to save on your brakes, but you aren't in fact really doing anything with that energy. It's not like you're saving it to be used up later, where this one actually can go back in and charge a battery. And I've seen it. I've got an older Prius, and if you're going down a really steep hill and you let off the throttle, you can actually see it starts to go back in and charge. You can see the direction, it starts to recharge the battery, and you can see your battery level increase. So if you don't believe that EVs are the answer for the future, hybrids are sort of a combination of both. You can get by with a reciprocating engine that can do, 80% of the work, or 50%, whatever you need, and then you can use your hybrid system to take care of the other percentage that you want.
Some wind turbines do this. They might need a kickstart to bring them up to speed.
Yep. Yeah, you could do the wind turbine, which you get it, because again, that's just an induction generator. So you can get that to spin and you can bring it up to speed as necessary. I don't have enough information. I've never been involved in the operation of a wind turbine. So I just assume they always start it up on their own with enough wind, but I don't know that for a fact. Nate probably has more background than I do.
Yeah, with enough wind they do, or with enough current, but sometimes when you want to do it at really low flow speeds, all you need to do is give it a little help.
Okay. I will
And then
warn you that help comes with a cost, because you got to buy those kilowatt hours. So
Doesn't take much.
doesn't take much.
No, you just have to get it up to like 10 or 12 RPM on those big ones, and then the wind will take it from there.
Okay. Yes. Yep. Yeah, and the other thing about those horizontal axis wind turbines, all the newer ones are designed to be facing the wind. So the blade, you can always tell the prevailing wind direction. The blade is facing the prevailing wind direction. Back in the day, they had these free spinning ones that the wind would push it, so it'd always be downstream of it. The problem with that is the tower itself would block some of the wind, so you're not as efficient. So almost all horizontal axis wind turbines, almost all of those are designed that they're upwind design. They're actually facing the wind. Now there are vertical axis wind turbines, and they orient themselves. They're basically spinning on this axis here, but they're not that common. They're not as efficient. There's a number of reasons for that, but you do see them, but they're not that common. I've personally never seen one other than like a research application where, I mean, you can go 5 miles up the road and see however many passive MK has, 14, 20 or something like that. What's that? The researchy type ones, they're called vertical access. So horizontal access is you have the shaft that goes into the generator is horizontal. Vertical access is this way. So the nice thing is the generator's on the bottom and the blades are up above. So all the weight bearing stuff is really low to the ground. That's a huge advantage. The downside is that those tend to be low to the ground. And where is the wind the best? It ain't close to the ground. Right. And there's also some things about efficiency of the blades based on the wind. There are some other problems. Again, I'm not a turbine blade designer, but you can find some stuff and they're really cool looking designs. They look incredibly cool. Whereas the horizontal access ones look pretty boring, but it's boring because the technology has sort of been optimized a little bit. So, and they're still putting wind turbines. They're talking about putting 50 megawatts. I think I told you this in Moscow, Maine. So they're still they're still commercially viable. Everybody thinks solar is the big dog, but all the big plants, at least in Maine, are going with wind. If you go to the Southwest, maybe it makes sense with solar, but in Maine, wind still does okay. It's just that it's harder and harder to find good solar resources. I mean, wind resources. With solar resources, as long as you have a distribution circuit and you keep your line or your output pretty small, it's pretty easy to connect. Where I just did the cost, an estimate for 120 megawatt solar farm that's going in Bradley, 13 million bucks just to build the interconnection system so that they can connect to the grid. That doesn't include them connecting. That's just for Versant to update their system. 13 million dollars. They still have to build a plant. It's probably be 50, 60 million bucks. So what's that? How many hydroelectric dams? I don't know the numbers, but if you go to, they really haven't decreased all that many. For a while they were decreasing them, but now it's held pretty stable. So if you go to ISO New England, they have a lot of the information on the generation. So if you look over here, this is in New England, and you can see hydro is this line right here. So 9% of the generation is hydroelectric. And it's kind of a joke, right? Because 9% is renewables. Isn't hydro technically considered renewable energy? So kind of a little bit odd, but hydro to me should be part of this pie as well. But I think in Maine, it's at least probably close to 15% of the generation in the state of Maine. I don't know if there is the resource mix, but this is telling you this is real time. So if you look at the date and time, right here, 4/06/23, this is a snapshot, but you can get real-time data. You can click on here, and this is telling you real-time costs of energy. Right now, if you wanted to make a buck, you could build the world's biggest battery system. This is about almost the lowest price you'll get for energy. $22 per megawatt hour. That is incredibly cheap. Do you remember what happened last September in California? Does anybody remember what they were charging per megawatt hour?
Didn't it hit 1,000?
1,354. It was pegged high. I have seen it in Maine, $700 per megawatt, but that's usually not because if you look at the demand, this demand is really low. Peak time in the summer will be 26,000, 27,000. We're less than half that. So right now, temperatures are nice. Nobody's got their lights on. This is when Versant makes their money because they don't adjust their kilowatt hour rate. They charge the same rate. But in the summertime, that's when they lose money. That's why your rates continue to go up. But that's why with renewables, and this is getting a little bit of a side topic, that's why renewables are so important. Why are renewables such a key for the future of the energy mix? There's one thing that is different between fossil fuel and renewables. How much do you pay for the fuel in renewables?
Fuel's cheaper. Or free.
Free. You pay for the sun? You pay
Oh,
for the
didn't it
wind?
count wood? Didn't it count wood as a renewable in there? So
Well,
maybe you
that would be, yeah, so that would be a biofuel. And so, yes, if you do talk about those biofuels, they tend to be a small part. So they are considered renewables, but some people say they deserve a special classification because you are burning something, you are releasing carbon. So it's not a zero-sum game, but the idea is that over the next 20, 30, 40 years, the carbon that is released from you burning it will be captured in new trees or grass or whatever. So there's a push, and again, this is not a hard and fast, but there's a push to focus biofuels more on the liquid fuels. So we still need cars, right? We still need dry vehicles. So ethanol, methanol, you would use more of the biofuels for that. And then we would do more of the, right? Solar doesn't cost a thing. The title that Nate does, how much do you pay for the tides coming in and out?
Nothing.
What's that?
Nothing.
Yeah, that's the key. You don't make money on these projects because they are cheap to build. It's that they have no fuel costs. Once a solar field is running, it's very expensive to build. If you look at the cost per megawatt hour, I mean, you need about 4 acres of land to get 1 megawatt. So you need a fair amount of land to be able to do that, where you could put up, main independent station, maybe 4 or 5 acres, and that's 550 megawatts. So an equivalent solar farm is going to be, I don't know, 5,000 acres or 4,000 acres to produce that. This takes up a huge amount of land. And to be able to fabricate something to do that is pretty tough. But the other problem is that that main independent station, as long as it's got fuel, it's ready to crank out megawatts. That solar farm at night, you're out of luck. Yeah, so the question is, where is the most expensive to maintain? And I don't actually know the answer. If I had to guess, solar is probably the cheapest, because other than cleaning the cells, and they do get dirty, and that does affect the performance, you need to clean them periodically. Not much maintenance to them. There's no moving parts. I mean, the transformers and stuff, you go out there and you make sure the grass is mowed so that it doesn't get around too much. But for solar, that's it. For wind turbines, you have gearboxes, you have rotating things, you have ice, you have a fair amount of mechanical systems. So there is some maintenance, and to exacerbate the maintenance of those things, your nacelle could be 200 or 300 feet in the air. Not easy to change the oil on something when you got to spend 20 minutes climbing a tower to get up there. And believe it or not, there's not an elevator in those. I think this is over 1,000. 9%. 18. Us meaning who? I think this is almost all, I don't know this for a fact, but I believe this is from the 3 operating nuclear plants in New England. There's 1 in New Hampshire, and 2 in Connecticut.
It's probably not the one in New Hampshire right now. They're in an outage.
Oh, they're in an outage? Okay.
Yeah, my roommate's down there doing maintenance. So
Okay. But those are big and they're carbon free. I didn't say they're no maintenance, but the thing is, the cost of nuclear fuel relative to the energy density is negligible. It's almost free. Not free, but almost free. But the thing about, and you're right about the nuclear power plant, is you have to ensure safety. So if you go to a natural gas plant, they do maintenance on it because they don't want it to fail, but they don't do near the maintenance that a nuclear plant does. For nuclear plants? Well, I don't know about overseas. I can tell you though that for the most part, nuclear plants are designed, and this is the newer designs, the Chernobyls where they basically put a prefab metal building around the nuclear reactor. Probably wasn't a great idea, but all the newer nuclear plants are designed with the concept that they can tolerate a worst case accident. There was one in Wiscasset. At the time when it was built, there was an Air Force base, I mean, a Navy base in Brunswick. And so the thought is one of those big Air Force planes would come crashing in to the reactor vessel, not the reactor vessel, but reactor containment. And that containment was designed to take a direct hit from one of these jets. The reactor containment vessels on these things are like 4, 5, 6 feet of concrete thick. They're actually designed that take the size of these containment vessels, and inside containment, they have a loop with water. And if one of those lines break, all the water that's in the reactor dumps out. You have this instantaneous change in pressure because the water lines, they're like running at 2000 PSI at 600 degrees. All of a sudden they're at ambient with no pressure. So inside containment would go to like 55, 60 PSI. And those containment structures are designed to not get damaged and only leak a certain amount. And they'd have to test those every 5 years. They literally bring in a bunch of compressors. They spend 3 days pumping them up. They make sure they don't leak, and then they would do that again. And nuclear is not dying in the United States. Does anybody know what just happened? Just this week, Vogtle Unit 3, I think, just came online. First time, I think in 15 years. Right here, 5 days ago. And can I do one of the most important things I'll ever teach you about nuclear power? You see these two big scary things here? What's that?
Terrible gas.
Terrible gas?
Yeah. Probably a nice little bolt now.
It's a cooling tower. Water
Condensation.
vapor. There's nothing to do with nuclear in here. That literally is because you have warm water that is sprinkled down at the bottom, and the design of this parabolic design forces air through it. So what comes out of there is just steam. Over here, kind of hard to see, but dwarfed by those scary looking cooling towers, that's the scary place. So every time you see a nuclear stuff, oh my God, nuclear reactor, it's a cooling tower. They'll always show a cooling tower. But that's what people have perceived to be as these big dangerous things. Maine Independence Station has cooling towers. They're just mechanical cooling towers. They're big fans. Because you have so much volume that you need to cool, and this is all natural circulation, that's why these plants have these big scary things. I went to a plant in Arizona. It was a coal-fired plant. It had these big cooling towers. So, but yeah, Vogtle, I think it's Unit 3, is going to be fully operational. And this was not one that had been designed 30 years ago and started construction, and then all the TMI, 3 Mile Island stuff happened. This is one that actually was built in the last 5 or 10 years. They started building it. So South Carolina had issues, but Georgia is somewhat full steam ahead. Well, it depends. Vogtle, I don't know. That's a swear word in German. I don't know. So, but yeah.
It's brought land and used, what happened in Chernobyl, like, yep, that's it.
Yeah, well, you know, the thing that happened in Chernobyl can't happen in the United States. And the reason why it can't happen in the United States is because their reactors are so big. They have like 2,000, 2,500 megawatt reactors. The biggest one in the United States, I think, is 1340 or 1350 megawatts. That their designs are so big, they can't get enough water to the reactors. So they use graphite. That's how they exchange heat. Well, what's the problem with graphite? At certain temperatures, it catches on fire and burns. And it's almost impossible to put it out. Water, last time I checked, doesn't do a very good job of catching on fire. So at a nuclear plant in the United States, you can't get a fire from the main system that actually keeps it cool because it's water. It's a clean, it's not deuterium, it's fluorinated water. It's a very light water that has some absorbing energy. In Canada, they use deuterium, which is a heavy water reactor, and that actually can make nuclear weapons, nuclear grade fuel, nuclear weapons fuel. Everybody understand nuclear power plant, the fuel is only enriched to 4%. They take pure uranium out of the ground and you need U-235, which is a specific isotope. You enrich that to 4%, and then you're good to go to make uranium fuel for a reactor. And the reason why it has to be enriched that way is that's the only one that once you get a chain reaction, it keeps going, it feeds itself. But it's only enriched to 4%. So no matter what you did, it can't explode. It's not explosive. Even if you go on a submarine, which that's like 90% enriched, that could be a bomb if it had a specific geometry, but it has to be made in a very specific geometry to give all that energy off at once. Anybody want to guess as to why you use 90% on a reactor on a Navy ship like a submarine or a aircraft carrier?
Base.
Base, yeah, gotta be smaller. And those are the only ones that use nuclear reactors. Everybody understand that it's a submarine and an aircraft carrier. Everything else uses, what's that? No, there was one, I think, was it the Eisenhower? Had like 7 reactors. But the newest version, I think, is it the Lyndon B. Johnson? They just commissioned it in the last year or two. That has 1 or 2 reactors. But can you imagine aircraft carrier running on diesel fuel? You'd basically have to have a gas station running alongside the entire time. You practically couldn't do it. Same thing with nuclear. With a submarine, you could have, you could put it as big as you want because you're underwater. But the problem is that you need oxygen, right? If you have gas, you need oxygen. You can get oxygen out of the water, but it's not readily available and need a lot of work. Nuclear doesn't burn anything, so you don't need oxygen. You just heat things up. So 3 Mile Island, they might have had an explosion, but it was not because the reactor problem. It was the same thing with Chernobyl. So 3 Mile Island, they had a gauge that was reading correctly, but the operators didn't believe it. So they kept shutting off cooling. And then they had part of the reactor that was exposed. So they were draining the reactor essentially, expose some of it. Once it gets exposed, it's too hot, and then it melts the structure that holds it in place. And at that point, there's nothing you can do. In Chernobyl, they actually had an explosion at the reactor. But in 3 Mile Island, the only explosion they were concerned about is you had this really hot material that came into contact with water, and it was actually splitting the molecules into hydrogen and oxygen. Well, hydrogen at certain concentrations is explosive just by vibration. So they were not sure when President Jimmy Carter, anybody alive when Jimmy Carter was president? It was in the 70s, but I don't remember this, but he went to 3 Mile Island and they were not sure, him driving there, it was going to cause a place to explode. So he was a real brave person to actually go there, because they're like, you could drive on here, sir, and you could show the place would explode and everybody would be dead. But he went on there and there was no problems, and that actually calmed the American public for a little while. But then there's a really old movie that talked about nuclear and it does all these explosions in the control rooms. You know what that's called? That's called Hollywood. That's not real. That whatever happened, I think it was called Silkwood. It was total BS. But if you want to watch a really old movie that I think won the Academy Award or an Oscar, you can take a look. Okay, good discussion. So let's get back to our conversation about torque. We still have a few minutes. So max torque occurs when the power transferred to R2 over S is at a maximum. Okay. Another way to say max torque is max power transfer. That's all it is. We're doing max power transfer. And max power transfer occur when the Thevenin equivalent impedance. So when we're looking on the stator side, and our stator impedance, equivalent impedance, matches our value of our R2 over S. Now we're going to do magnitudes. So our R2 over S, this is that our max torque is going to be equal to the magnitude of this expression. And then we can solve that for our max torque, or when our S or max torque occurs, and we can get that value. This is the value of slip where max torque occurs. Now we can substitute that back into our equation, and we can get that value there. So T max, 1 over 2 omega S, and we're not going to worry about that, but you'll notice that our R2 expression has been substituted in. You'll also notice the slip at maximum torque is directly proportional to our value of R2, the rotor resistance, because it's R2 squared. So, but the actual torque value is not dependent. So look over here. Do you see any R2 value? Nothing there. But let's go back over here, and it's there. So this tells us something pretty important. I can change the speed of where I get max torque by adjusting R2, but R2 doesn't affect the maximum torque. And so when we talk about a wound rotor induction motor, what you can do is you can inject a resistance in there that either increases or decreases this value of R2, and you can change the speed characteristics. So that's the wound rotor induction motor. And then this shows some of the characteristics of how I vary my torque value. Well, I shouldn't vary my torque. I vary the value where my pull-out torque occurs by increasing my resistance on the rotor, by adding more resistance until I get to this characteristic over here. If I continue to increase it, nothing's going to happen, right? Because my pull-out torque occurs at this value. These are called NEMA design characteristics. And so if you look at NEMA induction motor design characteristic, let's see if we can find a curve. Let's look at some images. These are the 4 types that you get. NEMA design A, B, C, and D. These, I think these are all called NEMA MG1. MG1 is the motor generator standard that NEMA produces. And remember how we were in lab? Remember how we said we were fairly flat? That's because we have a NEMA design B. A is where we show that curve and it goes up pretty high and peaks. And then we can see C and D. So C is basically increasing my resistance and I get a little bit of a dropping here. And D is when I start out with a maximum amount of torque. So remember that fan application where I've got that fan spinning and I got a lot of inertia? I might want to put a NEMA design B application to get that big mechanical load rotating. But for most purposes, you're going to specify a NEMA design B motor. Any of my mechanical engineering friends want to comment on that? Have you ever specified a different design than NEMA B?
Nope, it's usually our standard go-to.
Okay. Let's look at a typical NEMA MG1 nameplate, and let's see if we can see where it says design B. I don't know how legible this is going to be. Come on, I like to see a. So see, can you see right there? I don't know if you can see where my mouse is pointing, but if you zoom in a little bit, let me try zooming in a scotch. That's the NEMA design. That's the letter that it specifies. And like I said, most of the motors, I don't think I've ever seen a non-NEMA B is the standard, because our mechanical engineering friends, the characteristics that they really want are this. They want it to be able to start running, but if it's driving that pump that really doesn't start putting out any real power until you get a fair amount of speed, then this is where I want it to be operating. And take a look at the NEMA design B. Remember how the higher we get closer to synchronous speed, the more efficient the motor is? Well, look at the NEMA design D. I can start that all day, but look at the losses I'm going to get if I get to 100%. And the losses are because I've got a fair amount of slip there. So I've got pretty big I squared R losses as compared to the NEMA design B, which just because it's operating closer to synchronous speed is going to be a more efficient application. Good question. Why not use A? I don't know. I've never seen A. I'm not even sure that it can actually get to this value of torque. It might be that this is just too darn expensive. To get something like this, maybe that you need just such a low resistance resistor value that you need a lot of winding resistance. I'm guessing. I don't know. I've never seen one. Well, like I said, this is a very efficient one over here, and to get it to go incrementally into this direction, I'm assuming that you would need a lot of money invested on the rotor to do that, but I don't know that for a fact. I've never designed one of these. So hopefully, some of the stuff in the practical applications is making a wee bit more sense. All this nameplate stuff here. Starting to jive, because this is nothing fancy. It's only a 50 horsepower motor at 480 volt, definitely 3-phase. And the last thing I'll mention in this class, oh, remember we talked about service factor? This has a 1.25 service factor, so this can run 25% over its nameplate as long as you're in a 40-degree CMB. It can run at that value. There's an alternate service factor, but this is at 65 degrees C, much hotter temperature. Now, one of the things that, for those of you who are interested, if you get into bigger motor sizes, the vast majority of motors you'll come across will be 3-phase, probably 460 or 480 volt. You can get 208 volt, but it's not as common to get a 208 volt system as it is to get 480. Once you start pushing about 250 to 350 horsepower, you need to go up to a higher voltage. So once you get to 300 horsepower or so, like I said, you're going to get to a voltage that's medium voltage. It's rated at 4,160 volts. That's because the current, if you look at the current in here, let's see, where's the current? 61 amps. So if you multiply that by 5, you know, that's 300 and something amps. That's a lot of copper wire to get there. So it becomes impractical to do that at some point. So we just go with a higher voltage. So if we look at let's look at a 500, let's look at 400 horsepower and see the motor nameplate. Let's see if this one's any good. And no, this is kilowatts. Small ones. I don't know if we're going to be able to find one. Let's go 1,000. No, the NEMA stuff is just basically for electric motors. I don't believe that they include anything from there. So here's 1,000 horsepower. I don't know if you can see that, 4,000 volt. Like I said, the biggest one, I've actually seen a 2,000 horsepower motor that was a 480 volt, but that was at a facility that was built in the 50s. I can't imagine you could buy a motor this size. But even look at the current at 1,000 horsepower. I don't know if it has a current in here, 130 amps. Take that down to 480. You know, you're pushing over 1,000 amps of current. That's a lot. DC motors? To do what? A block load? Oh, brushless DC motor. Most brushless DC motors are really low power applications because they use power electronics to work. So those would be itty bitty. If you wanted to use DC motors, they do have them, and they make some pretty big ones, like train engines. They use DC locomotive ones. Those might be 100 horsepower, but those would either be series wound or a shunt wound DC motor, and they're really good for conveyors. So DC motors are really good for speed control and for locking in position, but I don't ever think you'll come across a DC motor in an industrial application. Yeah, they exist, but they're pretty uncommon. They used to be a lot more common, but more and more because of speed control with drives, you're better off to go with AC because they're so simple. Okay. Any questions? Hopefully I didn't get too off track. That's how I cut my teeth. I started working at a nuclear power plant. That's my very first real quote unquote job. Nuclear power plant no longer exists. That's my first job as an electrical engineer. Sorry, I didn't mean to use a weird expression, but never heard cutting your teeth? That's how you learn how to do something? Oh, I guess it's an old expression. All right. Okay, any questions? All right, have a great weekend. No lab next week. Not ready new, so I'll give you a little bit of a break. Take care, everyone.
Thanks, Paul.
Thank you.
Thank you.
Thank you.